Hi there. In this video we're going to look at how we can represent a transformation as a matrix and how we can interpret what transformation a matrix represents. So in our last video we saw what matrices were and we had a little glimpse into how matrices represent transformations, but we'll explore that in a little bit more detail in this video. So we've got a coordinate grid here. And we've got our two unit vectors, I hat and j hat. Now when we say unit vectors, it means they have a length of 1. And I hat and j hat are special unit vectors because they're the vectors that go 1 across and 0 up and down, and 0 across and 1 up. Now, why are these two vectors so special? Well, these are called the basis vectors, and that's because they're the basis of every other vector we use in our sort of normal coordinate grid, our Euclidean coordinate grid. So if we have the vector 3, 4, for example, remember that's 3 across and 4 up, but if we were to write it as a combination of I hat and j hat, well, this 3 means 3 to the right, which is exactly 3 lots of I hat, right? Oh no, that shouldn't be an A, that should just be a hat. And similarly, this 4 means 4 up, which is exactly 4 lots of this J. So the idea that any vector we have is a combination of these I hat and this j hat is going to be really important moving forward. But what that allows us to do is if we want to transform the plane, if we want to transform a shape that's on the plane, or a point, or a single vector, and we want to transform lots of different things in the same way, if we keep track of where I hat and j hat end up, that encodes all the information about this transformation. So let's have a look then at an example. Let's have a look at example 1. And this is the matrix, that's an enlargement. Scale factor 3, centre the origin. Now all of these matrix transformations are linear, which means they are centre the origin, and it means that it doesn't do anything weird like bend lines. It keeps lines straight. But yeah, so enlargement scale factor 3, centre the origin. So let's have a quick look at, first of all, what that will do to these two vectors, and then how we can write that as a matrix. So if we've got an enlargement scale factor 3, then this I hat is just going to get 3 times bigger away from the origin, right? So it's going to go there, it's going to end up at 3, 0, and we call that I hat with a little dash after it, or an apostrophe. We call it a dash in maths, but that just means it's the image of I hat, which is this after it's been transformed. And similarly, j is going to go to 0, 3, and that's going to be the image of j hat. Now, we said that in a matrix, all we need to do is keep track of what happens to I hat and j hat, and that's exactly what we're going to do. And so we have our matrix, and this first column is literally where I hat lands, so that's 3, 0, and this second column is literally where j hat lands, which is 0, 3. So this is the matrix that represents an enlargement scale factor 3, centre the origin. So we'll look at a few more examples of how we set these matrices up, and in our next video we'll look at how we actually use this, but I think actually being secure in setting this up is a really important step that we want to nail before moving on. So hold on to your hats because we're going to look at the next example. Okay, so let's look at our next example. So we're going to see if we can find the matrix that represents a rotation of 90 degrees clockwise about 0, 0, the origin. So clockwise, just to sort of remind ourselves, is in that direction. So let's see what happens. So remember, to write the matrix, we need to find the image of I hat and the image of j hat. Okay, so let's have a look what happens to I. Well, if we rotate it 90 degrees clockwise, about 0, 0, and we put our finger on the arrow at 0, 0, if we rotate this round, then it's going to end up at this vector here, which is the vector, well, it's 0 across, and it's -1, it's 1 down. Okay, so our first column is 0, -1, and I'll do that as dashed so we can see the difference. Okay, and then let's look what happens to j. So j hat, it starts up as 0, 1, and it goes to the right, and ends up here, exactly where I hat was before, interestingly enough. So then that's 1, 0. There we go, so this is the matrix that represents a rotation 90 degree clockwise about the origin. Okay, good. Okay, so let's have a look at this third example. This is a reflection in the line y equals x. As normal, if at any point you feel like you want to pause the video and have a go before I go through it, then please feel free to do so. That's sort of the best way to learn. Yeah, let's have a look at this y equals x. So let's draw on the line y equals x first of all. So the line y equals x is this line here. Okay, so let's see what happens to I hat and j hat when they're transformed. So I hat, if we reflect it in the line y equals x, well, it's going to end up exactly where j hat was. And similarly, j hat, if we reflect it, is going to end up exactly where I hat was. So I hat has ended up at 0, 1, and j hat has ended up at 1, 0. Okay. Good. Just for sort of curiosity, let's have a look at what would happen if we reflected it in the line y equals minus x. So we'll get rid of the image of I and the image of j, and this line. Let's draw on the line y equals minus x. Well, I hat then is going to be reflected. Now it's going down, and j hat is going to be reflected over here. So then I hat ends up at 0 across but 1 down this time, and j hat ends up at 1 to the left and 0 down. So maybe you've spotted a bit of a relationship between these two things. We've got 0, 1, 1, 0, and we've got 0, minus 1, minus 1, 0. And yeah, in a later video we'll sort of explore why this is the case here. Okay, so on to our final example of this video, and we're going to describe the transformation minus 1, 0, 0, minus 1. So even before we look at how we can apply these transformations to actual vectors, there's still a lot of information we can take from this. Namely that this first column vector here is the image of I hat, and the second column vector is the image of j hat. So let's draw all that information on a diagram. So I started off at 1, 0, and it ended up at minus 1, 0. And similarly, j hat started at 0, 0, 1, and it ended up at 0, minus 1. Okay, so we've got these vectors now, so now I just need to think what could have taken this pair of vectors this way and transformed it onto the pair of vectors that way. I think I've sort of given it away with my hand movement there. To go from there to there, the most obvious way to do it is by rotating it. Okay, so we could just rotate it 180 degrees and centre the origin. But there is another transformation that this could represent, or there's another way we could describe this transformation. This is just one transformation, but we can describe it in two ways. The astute among you might have noticed that we can also describe this as an enlargement scale factor -1, and that's the other way we can represent this transformation. Centre the origin. Okay, so good. If you managed to follow on with that, really good. Good. Now we'll do y = x first of all. I can cut that out.